Morning, and good day to all the learners. Today, I just want us to engage a little bit about organic reactions. My previous lessons actually I dealt with more about nomenclature of organic molecules, how do we name them, etc. But today, my focus will be based on organic reactions. More specifically, I'll be engaging on the alkanes as well as the alkenes, those ones that have a single bond, the alkanes, and those ones that have a double bond, the alkenes. So I just want you to learn more a little bit about how it goes about when you deal with their reactions, etc. Now, at the end of this particular lesson, you must be able to understand the movement of arrows in terms of electron density. The arrows are very important in organic chemistry. How you move them, it's also very important, because now when you have a half arrow, it's an indication of something as well. It's an indication of a single electron being moving from one element to another. So when we've got two arrows, actually it's a movement of two electrons. So the movement of arrows also is very, very important. So I'll also be dealing a little bit about how the arrows are moving from one molecule to another or from one element to another. The reactions of the alkanes that I'm going to deal with is the substitution reaction as well as the oxidation reaction. Okay, the name substitution in itself, it says something. You are removing something and you are replacing it with something. So that's quite easy actually. So it's just a matter of understanding that it's substitution. Something has to be removed from the organic molecule and it has to be replaced by something. And also I'll deal a little bit about oxidation, which is quite obvious, this one. And the product are always the same. It's just a matter of balancing the equation. And I'll also be dealing with the alkene, the one that has a double bond, the reactions of the alkene. So the reactions of the alkene, addition reaction, you are not substituting, you are not removing anything. You are adding on top of that particular organic molecule. So I'll deal with the hydrogenation, I'll also deal with halogenation, and probably most of those two, that they're the ones that I'm going to deal with in terms of addition reactions of the alkene. But it's quite obvious actually when you deal with the reactions of the hydrocarbons. So by hydrocarbons, I mean the alkanes as well as the alkenes, that when you say that the alkanes undergo substitution, it's quite clear that something has to be removed, because when you substitute, you're removing something. So when we say the alkenes, the ones that have a double bond, undergo addition, it's quite very clear that you're not removing anything from your organic molecule. You are just adding on top of that organic molecule. But in the process, you must take it into consideration that you are going to form a different organic molecule. For example, if you say that I'm adding a halogen to this particular alkene structure, it means that the product that you're going to form is no longer going to be the same. It's no longer going to be an alkene. It might be different. It might be a halo something, but it's no longer going to be your previous one that you started with, because now there's an addition of a new element into your organic molecule. So the product might be a haloalkane. When you add, for an example, a halogen, it will depend. When you add a hydrogen, which is a hydrogenation, to the alkene, the product might be an alkane. It's no longer going to be an alkene. So basically, you're breaking the double bond, you're forming a single bond. Now, I did say that, I didn't move so close now. My apologies for that one. Okay, this one. I did say that I just want us to also understand the basics of arrows, because majority of the time, people are making quite a lot of mistakes because of not so taking into consideration, I don't want to say not understanding, basically, not so taking into consideration the movement of the arrows, how important they are in any chemical reactions. So now, when you've got a full arrow, like a straight arrow, it's a reaction arrow. It shows you that, okay, you've got the reactants this side, and you move a straight arrow, then you've got the product on the right hand side. So that's quite clear. Now, when you've got a half-headed arrow it means that there's a movement of one electron. Now, when you've got a full-headed arrow says that there's a movement of two electrons. Now, this is a very important key. Arrows always move from a high electron density to a low electron density. I'm not sure if you quite heard about the word a nucleophile, because now when you move from a high density electron species, you're actually moving from a nucleophile to an electrophile. Electrophile is those ones that have a low electron density species. So basically, your arrow will always move from a nucleophile to an electrophile. From a high electron density species, which is very rich with electrons, and you move to the one that is poor in terms of electrons. Remember we said that under the alkanes, the one that have a single bond, they normally have, they will undergo one type of a reaction called oxidation. So oxidation of hydrocarbons is one of the most important organic reactions that you'll find out there. Normally what they do, if there's a burning of a huge amount of natural gas, gasoline and fuel, oil, which mostly involve combustion of hydrocarbons. Now, the reaction with oxygen leads to the formation of carbon dioxide and water with the release of ADs, usually heat. So basically, the product of combustion of an alkane, they will always give you carbon dioxide, water, as well as energy. Those will always be your product. As you can replace any hydrocarbon, an alkane, by the way, not any hydrocarbon, because it's alkanes that undergo combustion. Let me just emphasize that so that there's no confusion in it. So the alkanes basically are the ones that have a single bond. The alkanes, the ones that have a single bond, which are called alkanes, they're the ones that undergo oxidation, which is called combustion as well. Now they react with oxygen, and then the product is always, please take note that the product of combustion of the alkanes is always carbon dioxide, water, as well as the release of energy. I can give you any alkane there. You must know that the product is always carbon dioxide and water as well as the release of energy. It's just a matter of you understanding to balance the whole equation, because now it's a methane that is being provided there with a chemical formula CH4. I can give you propane and say that there's a propane, which is an alkane undergoing combustion in the presence of oxygen. So you must know that the product will always be carbon dioxide and water and the release of energy. It's just a matter of you balancing the whole equation now to make sure that there's equal number of oxygens on the left-hand side as well as on the right-hand side. So there must be that. So I wouldn't even think twice when I'm being given the oxidation of alkanes. I will know that what is the product. It's just a matter of seeing what type of alkane is being provided there. Are the number of elements on the left-hand side equals to the one on the right-hand side? Then I'll have to do a balancing, and then I will get the final product. I'll get the final reaction. But the main purpose is to understand that when you burn these particular alkanes, no matter which type of alkane are you burning, you will always get carbon dioxide, water, and the release of energy. Now it's just a matter of you trying to balance the whole equation to make sure that what is on the left-hand side is equals to what is on the right-hand side. That is the rule of a chemical reaction in terms of balancing. So I'm sure you're quite aware about that one as well. Now, there's an activity here. And when you look at this particular activity, it's an oxidation of methane as well in the presence of oxygen. Now, when you look at the two reactions, the other one says that it's a complete combustion. The other one at the bottom says that incomplete combustion. So there's a huge difference between the two reactions. The other one, basically, methane undergoes complete combustion because the product that we get there is the product that we are familiar with. Carbon dioxide, water, as well as the release of energy. But at the bottom one, the reaction is incomplete in a sense that there is also carbon monoxide there, there's also carbon dioxide, there's also water, there is something missing there. Energy is not there. But the presence of carbon monoxide as well in the process tells us that this reaction is not yet complete. It's still undergoing combustion because the final reaction is supposed to be the one at the top there, which shows clearly that your product are carbon dioxide, water, as well as energy. But when you look at the bottom, there seems that somehow is still forming the formation of carbon monoxide. There's also emission of carbon dioxide. There's no energy that is being released, so this particular reaction is incomplete. So the correct reaction then will be the one on top because it provides you with the well-known products of combustion of the alkanes, which is carbon dioxide, water, as well as energy. So please keep in mind about the products of oxidation of the alkanes as you go forward. Now, the second type of reaction that this particular type of hydrocarbon undergoes, which is the alkanes, is its reaction with the halogens, whereby the reaction actually takes place in the presence of heat. So I also want you to take note that no reaction will take place in the absence of heat or light. So what I'm trying to say is that as you formulate this particular reaction in your way to get the product, you must keep in mind that if we don't see the presence of heat there, if there is no presence of heat there, it means that that particular reaction will not take place. So the reagents, which are heat is part of the required reagents. It must be shown there in an arrow. If those particular is not shown, the heat is not shown there, it means that basically we don't understand this particular reaction because heat is extremely important for this particular reaction to take place. Now, this particular reaction is actually a substitution reaction. What do you mean by substitution reaction? One of the hydrogens is being replaced by one of the halogens. For an example, in this particular case, you've got chlorine reacting with a methane. So it means that, remember, methane has 4 hydrogens. And in your final product, how many hydrogens do we have now? We have 3 hydrogens. What does that say to us? It says that one of the hydrogens from methane was replaced by a Cl. Remember, this chlorine now has 2 Cl. It says Cl2. So that particular hydrogen that was replaced by one of the Cl, remember there are 2 Cl there, one of the Cl there is going to replace the hydrogen. That hydrogen becomes a living group. Where is this hydrogen going? This hydrogen is going to react with another Cl, and then it's going to form HCl. So this is a typical example of a substitution reaction of the alkanes. You just replace one of the hydrogens with a chlorine. But now, there's something that you must take into consideration. But when I look at your syllabus, I try to look whether you dealt with the major products or the minor products, because now this particular alkanes, at some stage, they will not enjoy the same chemical reactivity. So at some stage, there has to be a point whereby we deal with the major as well as the minor product. But I didn't want to go there yet because I went through your syllabus, then I couldn't find out whether you were managing to distinguish between the major product or the minor product. So I'll pause it there up until we meet at the Q&A session. In the Q&A session, I expect you guys to come and say that, but say we dealt with the major product and the minor product, then I'll elaborate further. For now, I don't want to cause any confusion. To say that, okay, let's look at the major product or the minor product, because I do know at the higher level, they do dealt with the major product as well as the minor product, because at some stage, this alkanes, they don't enjoy the same chemical reactivity. Because even the example, okay, let me emphasize on this one first before I can move. Because this one is just the methane, nothing can say. The 4 hydrogens are surrounded by 4. The the carbon is surrounded by 4 hydrogens enjoying the same chemical reactivity, so you expect to have one product there. Hence, I was talking about the minor as well as the major products. So maybe probably in your level is just where you are ending, but I'll find out from you guys on the Q&A session. So what is happening in this particular section? The way there's a substitution reaction. Please take note of the 3 key important things that are taking place here. First of all, you've got one of the hydrogens of stage 4 being substituted by Cl atom, substitution reaction. We agree about that one. Secondly, there are 2 types of bonds that are broken in this particular reaction. You've got the CH bond being broken. You've got the Cl and Cl bond being broken. There are 2 bonds that are also formed in this particular reaction. You've got the CCl bond forming. You've got also the HCl bond forming. Basically, in this type of reaction, in this particular substitution reaction, these are the 3 key important components that you must take into consideration whenever you undergo halogenation of the alkanes. There must be a removal of hydrogen and is replaced by a halogen. There will be a formation of 2 bonds that are formed. There will also be 2 bonds that are broken in the process. So those are the 3 key components that are taking place during this particular process. So please bear in mind, I can give you any halogen. Maybe I'll give you a bromine. So if I give you a bromine, it's very clear that 1Br is going to replace a hydrogen. And there's going to be 2 bonds that are also broken. It's going to be the CH bond as well as the Br bond. If I were to give you a bromine. Also in the process, there are going to be 2 bonds that are going to be formed. You're going to have a CBr bond formed. You're going to have a HBr being formed. So it can be replaced by any halogen. The process is still the same. Whatever that is happening when you're using Cl as well when you're using Br is still going to be the same. So this is a typical example of also a substitution reaction of an alkane. If you look at this particular one as well, you see that all the hydrogens, all the carbons, they have the same chemical reactivity. They join the same chemical reactivity. Hence, I said to you, you are going to get a monohalogenated product. Hence, I said to you, I didn't provide examples whereby there's a need for you to provide the major as well as a minor product. I'll be guided by you during the Q&A session. What I did, I just decided to provide examples whereby your alkanes are enjoying the same chemical reactivity, because even this one is CH3, nothing special. You're going to get a monohalogenated product, which is the one that is being provided on the right hand side. But once there can be a CH2 here, it quite changes everything. It becomes a different products that are going to be formed. Hence, I say that I can emphasize that during the Q&A session. You will guide me there. So the product is there actually. It's just a monohalogenated product, only a single product, nothing more. But look at what they still heat there, because this particular reaction is taking place in the presence of heat. So it's E is equal to HV. Now, when we deal with the alkenes, okay, let me put it clearly. When you deal with the alkenes, the one that has the double bond, mostly the type of reaction that is taking place there is the addition reaction. Remember the previous example, we dealt more with the substitution reaction as well as the oxidation reaction for the alkanes. But in this particular type of hydrocarbon called the alkenes, we are actually dealing with the addition reactions. You are adding something into the alkenes. In the process, you are breaking up that double bond. When you break up that double bond, you are adding something to the structure. So when you break a double bond, actually, it's no longer going to be an alkene. It's going to be something else. It will depend what type of addition reactions are taking place there. If it is hydrogen that is taking place there in the presence of this alkene, then we're going to form an alkane, the one that have a single bond. Now, if you are undergoing an addition reaction with a halogen there, the product that we're going to form there is the haloalkane. So the alkenes actually have a special, you see, this double bond actually is so special in a way that it has a sigma bond as well as the pi bond. And this pi bond actually is not like it's on a specific it's not like it is on a specific carbon in a double bond. This pi bond is actually delocalized over those two double bond carbons. It's not like it's placed specifically on this single carbon. No, it's delocalized. It's delocalized over those two double bond carbons. Therefore, because of the presence of the pi bond, the alkenes are nucleophilic, meaning that they are rich with electrons, and also they are more reactive than the alkanes. Why? Because of the presence of the pi electrons of the double bond. So double bond are more reactive than single bond. So the alkenes are more reactive than the alkanes because of the presence of the pi bond that is delocalized over those two double bond carbons. So they undergo an addition reaction, and in the process they break up that particular double bond there. So the first type of reaction that is undergone by the alkenes, the one that have a double bond, I'll always emphasize that so that we don't get to confuse the terminology. They undergo hydrogenation, meaning that reduction of the double bond. You are breaking up the double bond. You put a hydrogen there into the double bond, then you break up the double bond. So the electrons in the pi bond are used to form two sigma bonds. Once there's a two sigma bonds, then we broke up that particular double bond. So this hydrogenation reaction also requires a catalyst. Usually it's a transition metal in the form of PT. The product of hydrogenation, it gives us an alkane as a product. Remember, the double bond is broken into two sigma bonds. Those two sigma bonds are going to accommodate the two hydrogens. Once they accommodate the two hydrogens that are coming there, it means that now the structure is broken down. It's no longer a double bond, it now becomes a single bond. It becomes an alkane. So the product of hydrogenation of alkenes, it's an alkane. Please take that into consideration. It's very, very, very important. Here's a typical example of hydrogenation. You've got your alkene there, and then you are undergoing an addition reaction. Remember, there's an addition reaction that taking place in the alkenes. You've got the addition reaction of hydrogen, and then in the presence of catalyst. That PT is very important. So if you don't put the catalyst there, it means that you're saying that this reaction is very slow, will be very slow. It might not even go to completion. So remember, catalyst speed up the reaction. So the catalyst has to be there because it speed up the reaction. So in some cases, in some reactions, in the absence of a catalyst, those reactions actually, they don't even move. So I'm trying to say that please put the correct reagents as you are attempting to get your product. Hydrogen plus the catalyst in the form of PT, and transition metal actually. So please take that into consideration. Now, you've got your alkene there, and then they say that this pi bond is broken into two sigma bonds, and then there is an addition of two hydrogens circled there. So you form an alkane. It's an addition reaction. Nothing has been substituted here. Whatever that you started with as a reagent, they're still there. It's just that at the final product, you've got two additional hydrogens that is being added. So this one is a typical example of an addition reaction. Nothing has been substituted. Nothing has been removed. It was an addition of two hydrogens. For an example, if you look at the bottom reaction there, you realize that you've got propane 1 in. The fact that it says that E and E it means that it's an alkene, a double bond. Agreed. Okay, I forgot to put the catalyst there. There must be a catalyst, PT or something. My apologies, but it has to be there. Now, this particular prop 1 in, when you apply the presence of hydrogen there, the addition reaction of hydrogen, that particular reaction will form a propane. A propane, remember, it belongs to the alkene, meaning that you broke that double bond. You broke that double bond into 2 sigma bonds, and then they can accumulate those 2 hydrogens, and there is your product, an alkane. Now, the second type of reactions that we normally get from the alkenes is called the hydrogen halides. Hydrogen halides, remember, is the presence of hydrogen combined with halogens. So normally we symbolize it as HX. That particular X actually is standing for all the halogens, iodine, bromine, chlorine, and fluorine. So it is called hydrogen halides. Hydrogen halides mean that is a hydrogen in the presence of those halogens. So the halogens, remember, they are ones that belongs to group 7. Those elements that belongs to group 7 in your periodic table, they're the ones that are called the halogens. So there is an addition reaction of hydrogen halides with the alkenes. So I tried to put some typical example of what could be happening in the laboratory there. You could have your hydrogen halides in this particular big beaker there. Not a beaker, this one. In this particular flux there. And then there will be a movement of this particular hydrogen into, remember, it's an addition reaction. This hydrogen halides will move from this container there into the alkene. So basically, I'm trying to, in this particular case, I was trying to move from the theoretical point of view so that you view it differently, because sometimes when you're in laboratory, this is what is happening. And then because most of the time when we visualize them, we visualize these reactions in a form of theoretical written reactions. So I just wanted you to take into mind that in the laboratory, when we do these particular reactions, this is what is happening. You can have your hydrogen halides there moving into the second container there consisting of your alkene, and then this will take place for a certain amount of time, and then finally you'll have your product. So basically, the hydrogen halides are added as gases into the alkenes. They are not undergoing what we call hydrohalic acids. No. They are basically added as gases. Please take that into consideration. In the form of the type of bond that we are well known of is a covalent bond, HX. They are not undergoing this particular aqueous kind of a reaction where you've got your H being positive and your X. Remember, the X is symbolizing the halogen, your X being minus. This one, they undergo, basically they are added into the alkene as gases, not as hydrohalic acids. Please take that into consideration. Now, product of this particular reaction is an alkyl halide. That is the product of this particular reaction. Remember, the previous reaction, which was the addition reaction of hydrogen, the product was an alkane, a single bond hydrocarbon, an alkane. Now the product in this case of a hydrogen halides, which is added into the alkene, it is alkyl halides. Let's take an example of such a reaction. This is what we have actually. Remember HX. The X symbolizes your group 7 elements, which are the halogens. And then the rest of the naming now is called hydrogen halides. Now you've got your alkene undergoing addition reaction with your hydrogen halide. Remember, during addition reaction, that double bond is converted into 2 sigma bonds. Then these 2 sigma bonds can accommodate this hydrogen there. Remember the hydrogen HX, and it can also accommodate the X there. I want you to take note that whatever that is being added, it's added at the double bond carbons, because we are breaking the double bond carbon. Please don't confuse it. You'll see the H there is being added from the double bond carbon. Whatever that we do, addition reaction is taking place at the double bond carbons. So H there is added to this carbon here, which is the double bond carbon. Your X there is added to this double bond carbon. So I could rearrange them the other way around. I can put an X into this one, it's still fine. I can put an H into this one. There's no restriction there in terms of the rule. But whatever that is being added, because we are saying that the addition reaction of the double bond carbons, whatever that you are adding, it must be added to the double bond carbons. Not all those carbons that are not forming part of the double bond. So please take that into consideration. So, but I don't want you to say that, okay, it means that H must always be put to the carbon that comes first. No. I can put an X here. I can come and put an H there at the bottom. So we're not restricted into that one. We are only restricted into making sure that our addition reaction is taking place in a double bond carbon, not any other carbons within your organic molecule. I hope I'm clarifying it actually, so that we don't have any issues as we move forward. Now at the bottom there is a typical example of an ethene. An ethene is very clear that it has a double bond because of why? Remember we said that in most cases the alkenes, they will have E and E, which symbolizes that it's a double bond molecule. And then if it was an alkane, we are going to have A and E. But now E and E is an ethene, meaning that it's a double bond organic molecule. Now you add HBr. HBr is it's a hydrogen halide. Remember, HX symbolizes I, the X symbolizes IBrClF. So in this case, the X is being replaced with a Br. That is the reason why we got HBr. Now, remember, it's an addition reaction. You break the double bond into 2 sigma bonds. Those 2 sigma bonds, they can accommodate the presence of H. They can also accommodate the presence of Br. So at the end of the day, you've got Br there, you got H there. Please take note. Within this addition reaction, please don't put these 2 reactants, the H and the Br, in one double bond carbon. No. One must go to another double bond carbon, another one must go to another double bond carbon. Don't try and put them at the same double bond carbon. You'll be getting it wrong. And I said that the Br can be at any of the 2 double bond carbons. Doesn't matter. The H can be at any 2 double carbons. It doesn't matter. There are no rules at this stage. We don't know as we move forward if we are restricted or not. But currently, I can put Br here. I can put H here. It's still fine. But I cannot put Br and H at the same double bond carbon. One double bond carbon. No, I can't do that. Then the structure will be wrong. So please take note of that. As a typical activity where you've got your HCl undergoing an addition reaction with that particular structure there, which is a double bond structure, and then you know the product actually is going to break the double bond carbons, and then H will be one of those double bond carbon. Cl will also be in one of the double bond carbon. That was the story of. Remember, we started with substitution, whereby addition. My apologies. The alkenes, we started with the addition of hydrogen, and then we moved to the second one, which was the hydrogen halides, which was the second one, which give us the product alkyl halides. And now I want us to look at the last one for this particular lesson, which is the halogenation of the alkene. So we're going to look at the halogenation of the alkene. Halogenation of the alkene actually is giving us alkyl dihalide, meaning that in your product you'll have two halogens. So the presence of two halogens in your product, it says that we're actually forming an alkyl di 2. Remember the previous one, the reason why it was not a di, it was because it had one halogen in there, HX, one halogen. But in this case, we are having two halogens in the final product. So this one was alkyl halide. The other one that we're going to deal with now is going to be the alkyl dihalides. The reason is because you've got two halides within your product now. Okay, let me go back to the halogens. Now, you've got Br2 is reacting with the alkene, and then that double bond will be broken, and then the Br will be, one of the Br will be in that carbon which was previously in a double bond, and then the other one would be in this carbon which was part of the double bond as well. But because of the presence of two Br within that particular structure, then we are forming a alkyl dihalide. So in this case, actually, you must take into consideration that the reaction conditions for this reaction to take place, you need an unreactive solvent. You don't want a solvent that will be reactive. So basically, I should have put it there that you need an unreactive solvent next to the arrow, in the arrow there below Br. At the bottom there, I should have put unreactive solvent is required for this particular reaction to take place. Now, there's okay, you see now, the second one has put it very nicely there. CCl4 is an unreactive solvent in this case. So you've got your ethane, you've got your Br2, definitely you're going to get 1.2 dibromoethane. This particular product is called an alkyl dihalide. You've got your two of your Br in one of this double bond carbon. One of the Br will be here, another one will be there, and then your final product basically will be 1.2 dibromoethane. It is very important that that solvent is always there, because if we don't see the solvent, we are of the opinion that you don't understand the type of reaction that you are doing, because each and every reaction has its own requirements for it to take place. Otherwise, it will not take place. So it's very important that we take that into consideration as well. With that being said, thank you very much.